Hello, everyone. So today we will talk about Riemann sums. So remember, when we talk about calculus, there are kind of like two motivating problems. Two motivating problems. From kind of an abstract point of view, two things that people were trying to figure out how to do when they were trying to determine all these things. Well, one is what we spent the majority of the first part of calculus on. If you're looking at some curve, you want to say, okay, if I have a point on that curve, can I determine the equation of the tangent line? So find the equation of a tangent line. To a curve. And basically, this is answered using the derivative. So if we can find the derivative, then we have a method to find the tangent line to that curve at any given point. So we had lots of application problems. The other question that we generally focus on in Calc 2, but we'll look at the numerical technique at the end of this course, is if I have some curve, what else might I care about? So I have some curve and maybe I have 2 points, A and B. I would like to know, can I find the area below that curve between these 2 points, A and B? So can I find that shaded area? The majority of this is done in Calculus 2. It encapsulates the fundamental theorem of calculus part 1 and part 2. But we will look at a technique for solving this numerically, known as using Riemann sums. So this is what we look at in this section. So investigate a numerical technique for an approximate solution to this problem in this section. And actually, this method is used theoretically as well, because if we put this method together with our notion of limits, then it will lead us to understanding the indefinite integral, the definite integral, and the connection to the derivative, which is known as the fundamental theorem of calculus. But anyway, let's just focus on that numerical method. How does that work? So these are known as Riemann sums after the German mathematician Bernhard Riemann. So the idea here is to basically use a series of rectangles to approximate the area below the curve. Why rectangles? Well, rectangles have a very simple area formula. They just have the formula length times width. And, there are different ways to make this more complicated so that you have ideas of convergence and things converging faster. But we're going to take a pretty straightforward, simple approach in this section. One of the things we're going to do is we're going to create these rectangles so that we subdivide along the interval equally, which is not a assumption that you necessarily need to make. At higher levels, you talk about ways of partitioning the interval, and maybe not necessarily equal ways, but for us, we're just going to do it in the simplest way possible so you can see how this works. Okay, so the picture, basically, naively, there's kind of two ways, and we'll even talk about a third way at the end, to construct such an approximation. Based on if we want to start on the left-hand side or start on the right-hand side. So the picture, let's say we have a pretty simple curve, maybe something that looks parabolic. and we'll think about the two ways that we could approximate this. So these pictures are meant to look the same, so if they don't, it's just because I'm not great at drawing freehand. Okay, so let's say we have our point A and we have our point B. So we do the same thing over here. We have our point A and we have our point B. So basically our goal is to approximate the area between the x-axis and the curve on each graph using rectangles. So we've subdivided each one so that basically we're going to make 3 rectangles to approximate the area. But the question is, how do I want to make those rectangles? How do I want to figure out what their heights are? Well, basically I'm going to use the function to determine the heights, and we're going to assume that we're partitioning these in such a way that all the widths are equal, just to simplify our computations. So if we have a left-hand sum, what happens is we have kind of the left corner touching the graph, and then we want to move parallel to the x-axis until we get to the next point. And then move up and do the same thing, touch the curve, so that for each of these rectangles, the top left corner is what's touching the curve and giving the height for each consecutive rectangle. So for these 3 rectangles that I kind of have these 3 dots on the corners representing the heights of the rectangles. Now, if you did it starting at the right-hand side, you'd move on the right-hand side, and then you would touch the curve, and then move adjacent to, parallel to the x-axis, and then do the same thing. So you can see what's going on is we kind of have an under approximation using the left-hand sum. So we have the left-hand sum here. And on the right, we have what it would look like using the right-hand sum. So a pretty simple approach. So how do we do this in general? Well, usually there are some things that you want to know. You want to know formula for your function. You want to know some endpoints that you want to find the area between. And you want to know how many rectangles you're going to use. So let's write down what the general method looks like. So let's, in general, suppose this information is given to us using the following letters. So suppose we want to approximate the area below y equals f of x from x equals a to x equals b using n rectangles. Then from there, we can write down the width of each rectangle. And usually we use delta x to denote that. So delta just stands for change, as you might recall from science. And the way this can be figured out is by taking your endpoint b minus a and then dividing by the number of rectangles. And then that will give us our partition of the interval. So what will that partition look like? Well, we can use a bunch of indices. Basically, we'll have our starting point x0, then we'll have x1, then we'll have x2, and we'll have a bunch of different markings until we get to our final point, xn, which happens to be b. So x0 is another name for a, and xn is also b. Then we have a bunch of intermediate markings where we're essentially counting by the width of each rectangle. We're counting by delta x's until we get up to b. So how does this give us our areas? Well, it gives us an approximation for the area using the left-hand sum and also one using the right-hand sum. So basically our left-hand area approximation. Well, the width, since we've defined it in such a way that these are partitioned equally, is always going to be delta x. So the height of each rectangle is always going to be multiplied by delta x. So that can be factored out. So since each term will have a delta x, we can factor out a delta x. And then essentially inside the parentheses, we're just going to get the sum of each height. So if you go back to the picture, notice for the left-hand sum, I used the first value, the second value, and the third value. But there are 4 marks that were made on the x-axis. So the mark that was made on B was never used to compute a height when I'm using my partition there. So if this were, say, f of x, then essentially what I'm using is I'm using x0, x1, x2, and b is x3, and I'm not using that. And when I use the right-hand sum, I'm not using x0, I'm not using a, because the top left corner never hits on the right-hand sum. So what happens is the way we get our partition is we basically plug those values into the function to get the height. So I get f of x0 plus f of x1 plus f of x2, and I keep going, but I don't use the last point. What is my last value I'm using here? The one before the last one. So I'm adding f of x subscripted by n minus 1, and that is the left-hand approximation. And the right-hand approximation is going to be similar, but what happens is I'm not using f of x0 now, so I'm still using the same delta x, but I start at f of x1, and I go all the way to the end using the right-hand approximation. So I go all the way to xn. So, that might seem a little abstract for you writing it down in that way, but we'll do a few examples, and it's very concrete the way that we perform this process each time. So let's look at an example where everything's numbers, so we're not just using a bunch of letters and things like that now. So example, approximate the area below. So our function here, f of x, we're going to go with x times the natural log of x from x equals 2 to x equals 4 using 5 rectangles. So let's kind of do this in 2 parts. So for all parts, the width of each rectangle is going to remain the same. So that's our delta x value, which in this case is going to be 4 minus 2 divided by 5, which comes out to 0.4. So now basically what I want to do is I want to look at my starting value 2, and I want to kind of create my partition. So I'm partitioning my interval. I start at 2, and then I just count by adding 0.4 each time. So 2, 2.4, 2.8, 3.2, 3.6, and 4. And these are all the values that I'm going to use when I'm doing my left-hand sum and my right-hand sum. Those are the numbers that you're plugging into the function to get the heights of each of the rectangles. So let's say part A, we have our left-hand sum, or our left-hand approximation, let's say. This is given by our 0.4, which is our width, and then we want to plug each one of these into our function. So we're doing f of 2 plus f of 2.4 plus f of 2.8 plus f of 3.2 plus f of 3.6. Now, that function is going to change from problem to problem. In this problem, it happens to be x times the natural log of x. So this approximation really looks like 0.4 times 2 natural log of 2 plus 4 natural log of 4 plus, 2.4 natural log of 2.4. I can't read my own handwriting. Let me see if I can make that a little neater. 2 natural log of 2, and then plus 2.4 natural log 2.4 plus 2.8 natural log 2.8 plus 3.2 natural log 3.2, and then our last one plus 3.6 natural log 3.6. So you can type that all into your calculator to get an approximation. And when I do so, it comes out to 5.88 if we round to 2 decimal places. So let's go ahead and look at the right-hand sum. Now, usually you don't have to write down all of these different values, but I'm just doing it for completeness. But what is the difference going to be between doing the left-hand sum and the right-hand sum? Well, basically, the first term, f of 2, is not going to be used, and instead I'm going to be adding an extra term, f of 4. So instead now, my first thing inside the parentheses will be f of 2.4, and I will go all the way up until I reach 4 this time. So plus f of 3.6 plus f of 4, and then I'm done. And then again, I translate that into whatever our function I'm using, in this case, x natural log of x. So again, you plug all those values in, we get 0.4 times 2.4 natural log 2.4 plus 2.8 natural log 2.8 plus 3.2 natural log 3.2 plus 3.6 natural log 3.6 plus 4 natural log 4. And again, typing all that into the calculator, you can get 7.55 as an approximate value. So, we see that one of those is larger than the other. So we know the real area should be somewhere between those two values. So if we wanted to get an approximation for the area based on these two computations, we could say the approximate area is essentially their average. That's a nice, easy way to do it. So the approximate area below the curve is about, let's say, 5.88 plus 7.55 over 2, which is 6.715. And that would be a good approximation for the area there. So maybe we can make an observation. When is it going to be the case that the left area is smaller than the right area, or when do we know when one of the averages is going to be greater than the true value or less than the true value in terms of those areas? I mean, it depends on how complicated the function is, but one easy case, so observation, let's say, suppose f of x is an increasing function. Then what happens is, if you look at if your function's increasing, it's moving upward. If you look at a left-hand sum and you were making some triangles or rectangles, they would be below the curve. So a left-hand sum would be an under approximation of the true area. Whereas if you did the same type of curve but looked at doing it using right rectangles, those rectangles would now be above the curve when we make them. So a right-hand sum would be an over approximation of the true area. And if we think about x natural log of x, that would be an increasing function, so that's what we get in the previous example. So the left-hand approximation was 5.88, which is going to be less than the true area. a bound below, and the right-hand approximation would be a bound above. So we know the true area is somewhere in between. Kind of naive way to approximate that is just taking their average. In general, that's not going to be exactly correct, but it should be closer than either of the other two. If f of x were a decreasing function rather than an increasing function, exactly the opposite would be true. So if we had a decreasing function, a left-hand sum would be an over approximation, and a right-hand sum would be an under approximation. So let's just note that. Note that if f of x is a decreasing function, then the left-hand sum is an over approximation, while the right-hand sum is an under approximation. So there's one other method that you could use rather than just taking their averages. So we could also do this using midpoints. So another way to draw this same picture. So let's look at an alternative approach using midpoints. So basically what I want to do is, for each of the intervals that I construct in my partition, I want to use the midpoint of those partitions to construct my rectangles. So let's again say we have A here. So let's just do a very, very small case for the picture. So let's say this is A. We have kind of 2 in between, and then we have B, and maybe we just have, again, some parabolic looking shape. So maybe what I do now is, instead of using left and right, I look at the midpoint of each one, and then that is where I have my rectangle touch the curve. So I draw my 3 rectangles like this. So I kind of have a bit of each rectangle above and below the way this curve is shaped. And we can see that that's going to be a much better approximation than just using the left or the right, and we can kind of get a better approximation in one step, at least in these simple cases. So let's do the previous example using this midpoint idea. So let's write that down. Let's approximate the area for the previous problem using midpoint rectangles. So if we look at the partition again, we had 2, 2.4, 2.8, 3.2, 3.6, and 4. So I have a little bit of extra room. Hopefully it doesn't erase everything. Yep, sure did. So that was my partition last time. Now what I want to do is I just want to look halfway between each of those, and those are the midpoints I'm going to use. So I have 2.2, 2.6, 3, 3.4, and 3.8. And so those were the points I'd use to approximate this area. So now my area using, let's say, midpoint sums is 0.4, and then I do f of 2.2 plus f of 2.6 plus f of 3 plus f of 3.4 plus f of 3.8. And again, for each of those function values, you have to plug them into x natural log of x. But when you do that, I'm not going to write down that extra step. We have 6.70. So that's, again, fairly close, which tells us, so what did we get when we took the average of the left and the right? We got 6.715. So it's a little bit different, but it's still pretty close. And it looks like we had to do, a little bit less work to get this answer, which is a good approximation. So that's the midpoint method. So let's just go ahead and do one last example, and to kind of reaffirm what we've been doing here. So example, let's find the left, right, and midpoint area approximations for f of x equals e to the x from x equals 1 to x equals 2 using 4 rectangles. So again, for all 3 parts, we want to figure out what delta x is. So here delta x is going to be 2 minus 1 divided by the number of rectangles 4, which comes out to 0.25. So this gives our partition. So we've got 1, 1.25, 1.5, 1.75, and 2. And then when we want to do the midpoint, we're going to need to find halfway between, which you can add them together and divide by 2, add the consecutive boundary points. So we have 1.125, which is 1 plus 1.25 divided by 2, 1.375, 1.625, and 1.875. So those are the midpoint values. So then after that, everything's pretty easy. So the left-hand sum, the formula is pretty easy right now. We just plug in each value as the exponent of e. So we would get 0.25. For the left-hand sum, we use 1, 1.25, 1.5, and 1.75. So we would have e to the first plus e to the 1.25 plus e to the 1.5 plus e to the 1.75. So this comes out to about 4.11. For B, we have the right-hand sum. So this comes out, again, we have our width 0.25, and now we're plugging in all values except for the very first. So we have e to the 1.25 plus e to the 1.5 plus e to the 1.75 plus e to the second. And if you plug all that into your calculator and round to 2 decimal places, this comes out to about 5.28. So we know e to the x is an increasing function, so we know the true area is somewhere between that 4.11 and that 5.28. So you could add those together. If we average those, we could compare that to what we get for the midpoint. So just as an intermediate step, let me figure out what that is. So 4.11 plus 5.28 divided by 2 comes out to about 4.70, 4.695. So let's compare that to the result from the midpoint. So the midpoint we still have a width of 0.25, but now we're using those values on top. So e to the 1.125 plus e to the 1.375 plus e to the 1.625 plus e to the 1.875. So this comes out to about 4.66, so slightly lower. But anyway, that's a pretty nice overview of the approximation technique using left-hand sums, right-hand sums, and midpoint sums. So if you have any questions, please let me know and I can elaborate further. Otherwise, that's it. So this is Dr. Lennon signing off.